This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 1, Lesson 9, Altitude and Low Temperature Corrections. Everything so far assumes sea level standard air. Go up to 5,000 feet and the barometric pressure drops, the air thins, and three things change. The load constants shrink, the humidity ratio climbs for the same vapor pressure, and the chart itself shifts. We'll ground each correction, then rework a cooling load at altitude and watch the answer fall. Concept 1. Altitude thins the air. The handbook prints the barometric pressure relation as a function of elevation. Plug in 5,000 feet, and you get about 12.2 psia, versus 14.7 at sea level. Lower pressure means lower density. The pressure ratio is about 0.83, so a cubic foot of air carries roughly 17% less mass. The elevation correction section prints the same physics with slightly rounded coefficients. Same relation, don't read the two exponents as a conflict. Concept 2. The constants shrink. The 1.1, 4.5, and 4840 shortcuts all bake in the sea level density, so at altitude, they scale straight down by the pressure ratio. One rule, multiply each by P over P naught. At 5,000 feet, that turns sensible into 0.92, total into 3.74, and latent into 40.027, and the handbook prints those factors outright. The arithmetic gives 0.915. The handbook rounds to 0.92. Concept 3. The humidity ratio uses total pressure. W is 0.622 times the vapor pressure over total pressure minus vapor pressure. Drop the total pressure and the denominator shrinks. So for the same vapor pressure, the humidity ratio is higher at altitude. The saturation curve rises. At any temperature, the air holds more moisture, and the whole chart shifts up. That's why a sea level chart misreads an altitude state. Denver runs on the 5,000-foot chart. Chart number 4. Concept 4. The low temperature end. Refrigeration and freezer air sits at the cold side of the chart. The handbook's water saturation table stops at 32 degrees, the freezing point, where the basis changes. Below freezing, saturation is with respect to ice, not liquid, so excess moisture deposits straight onto cold coils as frost instead of condensing as dew. That frost blocks airflow and insulates the coil, which is why freezers need defrost cycles. Know it at the awareness level. The depth is week 3. Setup. Take the lesson 3 cooling coil, 2,000 CFM dropped 20 degrees, and move it to a 5,000-foot site. Same airflow, same temperature drop. The one and only change is the constant. Swap the sea level 1.1 for the altitude 0.92. Solve. At sea level, the load is 44,000. Swap the constant to 0.92, and the same coil at 5,000 feet is 36,800, 7,200 lower, about 16% less, because the thin air carries less heat per CFM. Notice the ratio of the two answers is just the pressure ratio. The whole altitude effect is that single factor. Turn it around, use sea level constants here, and you oversize the coil by about 20%. Traps. 4 ways altitude bites. 1. Sea level constants at altitude overstate the true load about 20%. Scale each by the pressure ratio. 2. The humidity ratio uses total pressure, so lower pressure raises W. Read altitude states off chart number 4, not the sea level chart. 3. Below 32 degrees, saturation is over ice. Moisture frosts, it doesn't drip. 4. It's a density effect, not a temperature effect. Scale the constant, never the delta T. Quick recall. At 5,000 feet, the pressure is about 12.2 psia, and the pressure ratio is about 0.83. Multiply every standard air constant by that ratio. 1.1 becomes 0.92. 4.5 becomes 3.74. 4840 becomes 40.027. The humidity ratio rises because it uses total pressure, so read altitude states off chart number 4. And below freezing, saturation is over ice. Golden rule. Scale by the pressure ratio and never trust the sea level chart at altitude. Next up, Lesson 10, the Week 1 capstone. That closes the Psychrometrics toolkit. Properties, the chart, the 4 process loads, mixing, evaporative cooling, the sensible heat ratio, and now altitude and low temperature. The capstone runs a mixed air, cooling, and dehumidification problem end to end. No new formulas, just the whole method in one pass. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at peprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.